Thank you.
Good morning to everyone. We can start with window investigation. My name is Željko Arbanas. I'm a professor of geotechnical engineering at the University of Rijeka, Faculty of Civil Engineering. And we can start with this session. We have at the start 5 presentations, and after that we have another one invited lecture. Every presenter have about 5 minutes to present their research, and I will invite Lorenzo Milan to present research with the title Challenges in the Characterization of Blocking Matrix Geomaterials. Please.
Thank you, Professor Arbanas. So I'll share my screen. Okay, can you see my screen?
Yes. Okay.
Yes.
Okay. Good morning, everyone. My name is Lorenzo Milan. In this presentation, I will deal with the challenges in the characterization of blocking matrix geomaterials, and I will describe an experimental campaign we carried out at Politecnico di Torino on such a heterogeneous material. And let's start saying that geological deposits are usually classified as soils or rocks, but in reality, a wide range of heterogeneous geomaterials with a blocking matrix fabric is found worldwide. And due to their variable composition and structure, these geomaterials belong to the so-called structurally complex formations, which are geological formations that make characterization and laboratory or in situ investigation particularly challenging. And following the definition proposed by Medley, these complex formations with a blocking matrix fabric consisting of rock blocks incorporated within a weaker matrix can be classified as beam rocks or beam soil, that stand for blocking matrix rock or blocking matrix soil, depending on if the contact between the rock blocks and the matrix is welded or not. While performing the analysis of these blocking matrix geomaterials, a lot of difficulties arise both in the geotechnical characterization and in the design of engineering works interacting with them. Starting from the geotechnical characterization, a lot of difficulties are usually encountered while shaping regular and undisturbed specimens to perform the laboratory tests due to the presence of rock blocks. And especially if the matrix is clay to marley, a lot of difficulties are encountered while collecting samples on site. In fact, standard coring techniques cannot be used since the cutting fluids will damage the matrix, which is very sensitive to water. And it was observed that dry coring techniques make almost impossible to extract the material from the drill bit without damaging it. So the only option is to collect samples on site is a manual coring. Even if this technique is not very efficient, it requires a lot of effort and it involves the most superficial portion of the rock mass only, which is the most weathered and fractured, and that means bigger difficulties later on while shaping the specimens. Moreover, we have to consider the difficulties in modeling the mechanical behavior of the heterogeneous material, which requires sophisticated analysis. And so all these difficulties over time have induced geopractitioners to consider oversimplified geotechnical models consisting in considering an equivalent homogeneous material with the mechanical properties of the weaker part of the heterogeneous one, so the matrix, and completely neglecting the presence of rock blocks. As an example, we can see here that a schematization of a slope stability problem involving a blocking matrix formation, and we can see the transition between a heterogeneous approach with a tortuous failure surface to a homogeneous approach with a regular failure surface. However, this common practice often leads to mischaracterization of the geomaterial, wrong forecasts of the geomaterial mechanical behavior, which means unexpected events during the executive phase and also safety problems, and finally, huge extra costs due to these unexpected problems. So, in light of all these observations, 2 main considerations can be made. First, a heterogeneous approach and the proper identification of rock blocks are necessary while studying geotechnical problems involving this kind of geomaterial. And then, if we want to study the mechanical behavior of the heterogeneous material, The only way is to refer to laboratory tests on reconstituted specimens, even if this practice is not without limitations. So at Politecnico di Torino, we carried out an unconventional experimental campaign with the aim of studying the influence of rock blocks on the mechanical behavior of the heterogeneous material. We started from an Italian beam rock consisting of limestone blocks embedded in a Marley to clay matrix. Some samples of this material were manually collected on site, and as standard coring techniques could not be used, and brought to the laboratory. And starting from these samples, the reconstituted specimens were prepared to perform the tests. Specifically, we performed isotropically consolidated triaxial tests, and we set up a procedure to be able to perform repetitive tests. So as I said before, sampling on site was not possible, so we had to consider reconstituted material, but we decided to use the actual natural material to prepare the matrix of the reconstituted one. So we dissolved in water a big amount of the natural material. We sieved it using a 75 micron sieve to collect the finest fraction only. And then we heated it in the oven very carefully by constantly ensuring a uniform heating of the material up to a water content of the 80%. Then the material was split in two parts. One of them was used to obtain homogeneous specimens, and to do that, we artificially consolidated the material using a consolidometer up to a maximum vertical effective stress of 500 kilopascal, and through a consolidation process that lasted 44 days. And from the consolidated material, we obtained the specimens, the homogeneous specimens, by extrusion. Then we followed a similar procedure to obtain heterogeneous specimens. In this case, we mixed in the steel cylinder of the consolidometer gravel blocks with dimensions between 2 and 4.75 millimeters, in such a way that at the end of the consolidation, a volumetric block proportion of the 25% was present inside the consolidated material. This value was chosen following some previous studies on similar geomaterials, which were providing conflicting data about the minimum threshold of the block content above which an influence on the mechanical behavior can be observed. And since this value varied between 10 and 20%, we decided we wanted to stay higher than the actual minimum threshold, but we wanted to consider a value representative of many beam rocks, so we defined 25%. And so again, 44 days of consolidation, and at the end of the procedure, we obtained specimens with dimensions almost equal to the standard ones. I said almost because in this last step, we faced some problems. During the extrusion, when the sampler encountered a rock block on the external surface of this small cylinder, which will be the specimen, it was dragged down, creating a furrow on the external surface. And so the first result of this operation was this one shown in figure A. We noticed that this condition would have produced a high risk of breaking the membrane that isolates the specimen during the test. And so we decided to manually regularize the geometry of the specimen as far as possible by filling all the voids using consolidated matrix. So the final result was this one shown in figure B, which is a not perfectly linear, not perfectly regular cylinder. As regards the tests, we performed 6 triaxial tests. 3 of them were performed on the homogeneous material to define a reference configuration that describes the mechanical behavior of the matrix only. And by considering the failure states of these tests, we obtain a quite linear failure envelope, which you can see here in the continuous blue line, with an R-square very close to 1. And we computed the corresponding Mohr Coulomb strength parameters. Specifically, we obtained 12.3 kilopascal as cohesion and a friction angle of 15 degrees. Then, using the same radial confinements, so 50, 100, and 200 kilopascal, we performed the corresponding heterogeneous tests. Again, we obtained a quite linear failure envelope with an R square very close to 0.99, and we computed the strength parameters. We can notice that even if the ultimate strength is not very affected by the presence of rock blocks, being the confinement constant, the overall influence of the presence of rock blocks is significant, and even a rather low block content induced significant modifications in the strength parameters. Specifically, we obtained an increase in the friction angle of the 23% and a decrease in the cohesion of the 20%. Then, if we focus on the deviatoric stress versus axial strain plot of the 6 tests, we can notice some additional informations. We can notice that the failure strain is not very affected by the presence of rock blocks, while as regards deformability, a lower deformability was always observed for the heterogeneous specimens, meaning that the blocks strongly influence the deformability of the blocking matrix geomaterials. Finally, especially for low confinements, we can notice that the dilatant and softening behavior of the clay matrix was reduced by the presence of rock blocks, which did not allow the development of the shear band and the localization of the deformations. As we can see here on the right, where the pictures of the 6 specimens at the end of the tests are shown, we can see that the homogeneous specimens confined at 50 and 100 kilopascal failed, showing a visible shear band, while the corresponding heterogeneous specimens failed in a more widespread manner. So the rock blocks did not allow the development of the shear band and allowed the material to retain a post-peak strength almost equal to the peak one, meaning that the rock blocks play a major role in governing the failure mechanism of the blocking matrix geomaterial. At 200 kilopascal, even the homogeneous specimen failed with this barrel-shaped deformation, while the corresponding heterogeneous specimen failed with this very squat deformation. So at the end of this discussion, I would like to tell you what are the following research activities that constitute the short-term future development of this study. We are currently working on additional triaxial tests using different volumetric block proportions and radial confinements. And specifically, these radial confinements will be lower than 50 kilopascal to investigate if a nonlinearity of the failure envelope can be observed for these very low stress states. Even if I can already tell you that we performed a test at 25 kilopascal and on the homogeneous material only, and we obtain a perfectly linear failure envelope. And then we would like to set up a numerical model using all the information provided by the previous tests, able to simulate the triaxial tests by means of a proper calibration of all the input parameters. And hopefully this numerical model will allow us to perform parametric analysis and extend the field of applicability of these observations. Thank you very much for your attention.
Thank you, Lorenzo. It is very fun presentation and very original. I have some questions, but we can discuss later. The second presentation will be swelling and swelling pressure in clay landslide, experimental data and model simulation. And this presentation will be held by Fatsaneh Galamzan. I hope that my pronouncing is okay. Please.
Okay. Can you see my screen?
Yes, yes.
Okay. Good morning, everyone. I am going to present the experimental results and model simulations of the influence of pore fluid composition on swelling properties of the tectonized clay shelves of Costa delle Gavette landslide in the southern Italy. The motivation of this study can be summarized as follows. In this slope, the natural pore fluid is an aqueous ion solution, which at 5 to 10 meter depth, the concentration is very close to seawater, and it decreases towards the ground surface in the stable formation. The concentration is much lower in the landslide. This soil is characterized by wide variation of plasticity and activity. In order to evaluate the effect of pore fluid composition on the volume change behavior, soil samples with different liquid limit were reconstituted with distilled water or concentrated solution and compressed in odometric condition. As you can see in these figures, by decrease of liquid limit, the effect of pore fluid composition on the volume change behavior decreases dramatically. To analyze the effect of exposure to distilled water, soil fractions with different liquid limit were reconstituted with salt solution and compressed in odometric conditions. And the tendency to swell was induced by unloading and exposure to distilled water. The chemically induced swelling was permitted in a set of specimens to evaluate the swelling displacement, which will be denoted as free swelling test, and was prevented in another set to evaluate the swelling pressure, which will denote as swelling pressure test. The chemically induced swelling is very large in most plastic soil, and it is negligible in the least plastic one. Swelling pressure as well attain different values, but as you can see, it is large also for the least plastic soil. In addition, exposure to distilled water is known to decrease both critical state and residual friction angles. Here, the analysis have been focused on the soil behavior with the smallest chemomechanical response, which has been extracted from borehole S9. Thus, the effect that have been evaluated is certainly underestimated. That was the motivation of our work. Here is the outline of my presentation, which include problem formulation and proposed two-dimensional model, the validation of the model with experimental odometer tests and sample extracted from Costa de la Gaveta, the effect of swelling pressure on slope stability, and finally conclusions. Saturated clay is composed of the fluid phase and the solid phase. The solid phase has clay particle, adsorb water, and adsorb ion. The fluid phase has pore water and dissolved salt. Water and salt can diffuse through the porous medium. In addition to mimic the adsorption-desorption of water, we assume that a semi-permeable membrane surrounds the clay particles, which is permeable to water only. Thus, the following balance equations have been considered: the momentum balance for the whole porous medium, the mass balance of pore water in the fluid phase, the mass balance of salt in the fluid phase, and finally, the mass balance of absorbed water in the solid phase. We have implemented a two-dimensional plane strain element with 8 nodes. In this element, in the corner nodes, we have 5 degrees of freedom, include displacement, pore pressure, salt concentration, and mass of absorbed water. And in the middle nodes, we have only displacement as degrees of freedom. In this model, we have introduced an innovative elastic energy, which takes account of mechanical part and chemical part. The mechanical part is a polynomial function, which takes account of elastic anisotropy through a fabric tensor B. The novelty of this elastic anisotropy is that both bulk modulus and shear modulus depend on stress state and salt concentration. The yield function was deduced from the classical chem-clay model, which depends also on chemical potential of absorbed water. To obtain better agreement with the experimental results, the shape of the yield function is such that for highly overconsolidated sample, we have a smaller peak strength respect to chem-clay model. In the experiment, the soil samples were reconstituted with salt solution or distilled water, and then it was put between two porous stones and submerged in a reservoir which was filled with the same solution as soil sample. And mechanical consolidation and swelling was induced by increase or decrease of mechanical load, and chemical loading and unloading was induced by renewing the cell water. Because of symmetry, we have simulated only half of the odometer test. The cell fluid was simulated as fictitious porous stones with a high hydraulic conductivity and diffusion coefficient in order to prevent the salt concentration gradient in the reservoir. Also, the preparation of the sample with 1 molar solution was simulated by exposure of the sample to 1 molar solution under isotropic stress equal to 10 kilopascal. Here you can see the comparison between experiment and simulation. For a sample prepared with distilled water and a sample prepared with 1 molar solution. Here you see the result for mechanical loading and unloading. And on the right-hand side, you can see the result for the combination of chemomechanical loading and unloading. As you can see, there is a good agreement between simulation and experimental results. We have evaluated also the swelling displacement and swelling pressure in this specimen. The soil was reconstituted with 1 molar solution and loaded to 1,200 and unloaded to 300 kilopascal. And the swelling displacement and swelling pressure have been evaluated. In particular, you can observe that although the amount of swelling displacement is negligible, the amount of swelling pressure is significant. To evaluate the effect of elastic anisotropy on swelling behavior of soil, we have considered 3 different sets of components for the anisotropy tensor. In particular, we have considered an elastic isotropic response, a response in which the vertical stiffness is larger than the horizontal one, and a response in which the horizontal component is larger than the vertical one. Here you see the comparison between experiment and simulation for the swelling displacement and swelling pressure for different elastic anisotropy. As you can see, we have better agreement when we use the elastic anisotropy with larger components in the horizontal direction. Here you can see the model predictions for the time evolution of horizontal stress during exposure to distilled water to evaluate the swelling displacement and swelling pressure. In particular, you can see that during free swelling test, the increase of horizontal stress is small and it is negligible when we use the elastic anisotropy with the larger component in the vertical direction. But during swelling pressure test, the increase of horizontal stress is quite large for all cases of anisotropy. The amount of removed sodium ion has been measured during free swelling test and swelling pressure test when we expose to distilled water. As you can see in both tests, the measured ion removal is initially faster than the simulation. Here you can see the amount of salt concentration inside the sample and porous stones during different duration of exposure to distilled water to evaluate the swelling displacement. As you can see, in the porous stones, in the vicinity of cell fluid, the decrease of salt concentration is very fast, while in the sample, the decrease of salt concentration is quite slow. And the maximum salt concentration occurs at the middle of the sample. The model fully takes account of the diffusion of salt out of the sample and porous stones, and the counterflux of water inside the sample due to swelling. Okay, after seeing the experimental results and model simulation of swelling pressure due to exposure to distilled water, let's make some considerations on the effect of swelling pressure on landslide movement. To this aim, we have simulated a schematic slope with the dimensions shown in this figure. A pre-existing circular failure surface has been considered. This is a simple and preliminary model in which the two-phase nature of clay has been neglected. In addition, the chemically induced volumetric strain has been simulated through the variation of temperature. The increase of temperature simulates the exposure of the slope to distilled water, and decrease of temperature mimics the increase of salt concentration. We have evaluated the stiffness of the soil based on swelling pressure and tangent odometric modulus. For the friction angle, we have considered two constant values, which for the stable soil and along the slip surface. And we have neglected the effect of changing salt concentration, which affects the friction angle for the sake of simplicity. During chemical loading and unloading, we have monitored the relative displacement of a node in the middle of the slope. Here you can see the relative displacement of this node. As you can see, by increase of temperature and decrease of temperature, which simulates the exposure to distilled water and increase of salt concentration, this increase and decrease leads to a residual displacement in the node. This means that swelling leads to an increase of horizontal stresses in the slope and to irreversible displacement along the slip surface. This is important in first-time landslide because the displacement leads friction angle to decrease towards residual value. And also this effect superposes to the decrease of friction angle due to exposure to distilled water. Thus, the combination of increase of horizontal stress and decrease of friction angle could explain the onset of first-time landslide. In the initial condition, you can see when gravity is activated, the maximum displacement occurs at the top of the slope. By decrease of salt concentration in the slope due to exposure to rainwater, the slope moves along the slip surface. And by possible increase of salt concentration, you can see that it leads to increase of displacement of the slope, especially at the top of the slope. So we can draw the following conclusions. This work provides a complete picture of the possible effects of chemical interaction between the solid skeleton and pore fluid and index properties, one-dimensional compressibility and shear strength. Even the least active soil exhibits significant swelling pressure due to exposure to water. The experimental results were subsequently used for calibrating a constitutive model, which is capable of fully considering the chemomechanical interactions and the effects of anisotropy and for including a more sound yield surface. The model was implemented in a finite element framework that considered all coupled phenomena, namely momentum balance of the whole solid, mass balance of pore fluid and dissolved salt, and finally water adsorption desorption. A preliminary and simplified analysis of a schematic slope in which chemically induced swelling was simply simulated as a temperature increase of the soil in the sliding mass showed that chemically induced swelling can have an important role in a slope stability, and thus it should be carefully analyzed and taken into account. Future development will concern a complete analysis of the landslide, taking into account the chemical effect both in the clay mass and along the slip surface. Thanks for your attention.
Thank you for a very interesting presentation. For questions, we will have time later. We can go to the next presentation. It is a paper prepared by Veronica Pazzi and Stefano Morelli. Geophysical methods applied in the study of stiff clays and flysch formation, a review. And the presenter will be Stefano Morelli. Please, Stefano.
Okay. Can you see my presentation?
Yes, yes.
Yes, yes.
Okay. Good morning, everyone. Today, I want to present you the result of a review work about geophysical methods applying the study of stiff clays and flysch formation. This presentation will focus on four main topics. The first one is the main research question in landslide studies and the purposes of this review work. Then the open drawbacks according to an important review of 2007. And finally, the main results in synthesis and some conclusions. Starting from the main research question in landslide studies, we can identify 6 main questions. The first one is how large are the boundaries and how they can change over time. Then how depth is slip surfaces. And then are there more than one slip surface? And then the third one is which are the constituent materials? How are the materials in homogeneities distributed and which are their properties? Which are the deformation processes? And are there any precursor before the triggering time of clear evidences before the occurring? Active and passive geophysical technique can be employed where there is a significant detectable contrast in physical properties of different lithological units. But however, the application to study, characterize, and monitor landslides is the challenging issues up to date. Therefore, the academic references available are very, very, very few. And in a review carried in 2007 about the geophysical investigation of landslides, some drawbacks were clearly identified. This review was carried out by JONGMANS and Garambois in 2007. They considered papers after 1990. And these papers were published on peer-reviewed journals and written by scientists, as the same author said. Only a limited number of proceedings from international conference were considered, and the main goals of this paper was to improve the exchange of expertise between geophysicists, geologists, geomorphologists, and geotechnical engineers. So also in this paper highlighted 5 drawbacks. In particular, they underline how geophysics have to make an effort in the presentation of results. The drawback 2 was the resolution and the penetration depth of each method are not systematically discussed in an understandable way. The geological interpretation of geophysical data should be more clearly and critically explained. The challenge of geophysicists is to convince geology and engineers that the 3D and 4D geophysical imaging technique can be valuable tools for investigating and monitoring landslide. And for this reason, efforts should also be made towards obtaining quantitative information from geophysics in terms of geotechnical parameters and also hydrological properties. Starting from these 5 open points in 2019, we carried out a new review to analyze the geophysical community efforts in overcoming all the drawbacks we said before. We analyzed, in this case, about 120 open access papers published after the first review in 2007, considering peer-reviewed journal and without taking into account proceeding of international conference. We adopted the materials landslide approach, of course, according to the Untitled classification in 2014. This classification was an adjustment of the previous most worldwide and famous classification on Cruden and Barnes in 1996. And so that this means that we divided our studies in two classes, considering rock landslide and soil landslide. Starting from this last review and given the topic of the conference, this work focuses on the application of geophysical methods to study landslide occurred, of course, in flysch and stiff clay formation in the Mediterranean area, as we consider in this symposium. We underline that we considered stiff clays and flysch, but also all the sedimentary material in geological connection and in physical continuity with their depositional environment. We consider also flysch-like depositional sequences because in some papers they did not describe exactly the formation, and so we try to understand if it was a flysch or it was not a flysch. So it was very hard work to understand the real comprehension of the material. Thus, the 41% of soil landslide type, and only the 15% was rock landslide. And we considered in this case 15 news papers from the last 2 years, from the 2019 and today. To quantify the efforts done, we adopted a level scale. We considered two symbols, plus, minus, and an acronym ND. The plus means that many or some efforts were made. Minus means that insufficient efforts were made to overcome the limitation, while the ND acronym means that the point is not discussed. As you can see in this slide, all the selected landslides are visualized in black dots in a geological map of the Mediterranean area. The number of slides is less than the work we consider, since some landslides are presented, analyzed in more than one work. They consider some different approaches, different instruments, or they analyze different parts of the same landslide. On the other hand, red dots indicate other landslides occurring in slope and stiff clay formation, but their results were not published in journals, but in proceedings and book chapters. So these publications were not considered to be in line with the other kind of presentation articles in 2007. Of course, we can say another observation, of course, in this map, just before to continue, because we can see there is not a uniform distribution of studies. This, of course, is in relation to the fact that formations, geological formation, different distributed in the Mediterranean area, but of course there is other consideration to do. For example, that geophysical technique could not be considered economic in some countries if compared with more traditional technique, and so in some places they considered only methods limited to a specific engineering problem, to solve a specific engineering problem, so they consider a very few kind of methods and instruments. In some countries, On the other hand, they used to publish only in proceedings or in conference and symposiums materials, so they were not very peer-reviewed journals. So we can notice that active and passive seismic technique together are the most employed. But considering the single technique, the most used is the electric resistivity tomography. In the 57% of the analyzed paper, only one geophysical method is presented and discussed, even though in all the analyzed work, the geophysical methods are integrated with other survey technique data. In the half of the analyzed paper, there is a tendency to show and present the results more objectively. This is related to the drawback one. This could be possible thanks to the development of new 2D and 3D software that allow the integration of data from different sources and survey. Moreover, great efforts were made to improve the geological interpretation of the geophysical data and to explain it more clearly and critically. This is, of course, related to drawback 3. On the contrary, drawback 2, 4, and 5 were not discussed and presented in the analyzed paper, meaning that the resolution and the penetration depth of each technique, the potentiality of 3D and 4D approaches, and retrieving quantitative information in terms of geotechnical parameters and hydrological properties were not discussed and presented in the analyzed paper. So, coming to the conclusion, we can say that to study landslide occurred in flysch and stiff clay formation in the study area, active and passive seismic methods are the most employed, but considering a single technique, the most used is, in any case, the electric resistivity tomography. Moreover, many efforts were made to improve the geological interpretation. A very important effort were made to improve the geological interpretation of geophysical data and to explain the interpretation more clearly and critically. That was the drawback 3, as I said before. But while some efforts, but not still enough, I can say, were made to show geophysical results more clearly, as was related to the drawback 1. And finally, you can say that very few efforts were made to overcome the other 3 drawbacks, 2, 4, and 5, as I said before. That means to systematically discuss the resolution, the penetration depth of each method, to demonstrate the usefulness of 3D and 4D approaches, and to obtain the quantitative information in terms of geotechnical parameters and hydrological properties from geophysical data. That was the drawback 5. So that's all. Thank you for your attention. For more information, you can directly contact my colleague Veronica Pazzi, which was the first author of the paper presented here in this symposium.
Thank you, sir. It is very interesting presentation, but I think that 15 minutes is not enough for a review paper, and we can show only parts of your paper. But thank you for this. Next presentation will be Darrell Baidar slope stability, experimental characterization and analysis. Presenter will be Sabine Khalil. Please, Sabine.
Good morning, everyone. I will be presenting. Okay. 1 second. Sorry. Sorry for technical. Okay. Can you see my screen now?
Yes, yes.
Yes, okay. I'm presenting a case study about Darrell Baidar slope stability, an experimental characterization and analysis. the incidence of landslides is very common in the hills and the mountains of the Arab regions, especially in the Mediterranean country, Lebanon. Every year, and as a result of combined actions of natural and man-made factors, floods and landslides yearly cost around from 10 to 15 million US dollars in a small country like Lebanon. Topography, geology, and seismic activities might be the main causes, but climatic conditions and as torrential downpours and aggravated by human activities such as deforestation and cultivation and construction destabilize the already fragile slopes. We can see here some examples of the slope stability problems in Lebanon triggered by climatic conditions and by human activities such as constructions. For this reason, many studies were conducted in the past years in order to increase awareness about slope stability and mass movements in Lebanon. In the same context, this presentation shows a study of Dahr el-Baydar slope that has experienced many failures and seismic movements. Dahr el-Baydar is located in the Mediterranean country, Lebanon, as I said before. It is located in the inner parts of its mountains, and it constitutes a linking point between the coastal areas and the inner areas of Lebanon and to the Arab regions also. For this reason, projects have been conceived to improve this area. For instance, Dahr el-Baydar hosts an under construction road named the Pan-Arab Highway that is designed to connect Beirut, the capital and the largest city in Lebanon, to neighboring Arab countries. However, slope stability problems had caused delays at several instances in the achievement of the highway works. Therefore, the aim of the study was to identify the causes that led to failure at the slope using geological, geotechnical, and geophysical investigation. For the site geology, the geological maps show that the geological formations in the site were the Cretaceous formations, C2A, C2B, and C3, that are formed from different types of soils as the sand, clay sand, sandstone, and marl, as we can see in the geological maps here. And we can see also that the Cretaceous formations are based on the Jurassic formation, which is the limestone, the blue limestone. The geological formation show also the presence of some seismic faults in the zones, as I am showing now on the picture, of three main faults. It is suspected that the system of faults is active, but however, their individual activity is difficult to trace due to the lack of instrumentation on site. For the site hydrogeology, the piezometers installed during the investigation showed that the water table is deep, but it was detected in some other inspections that an infiltrated water appears on the surface of the ground. This was only an inspection and no further hydrogeological investigation was done. It is suspected that it is coming from the snowmelt runoff from the surrounding mountains, and that causes the water level to rise to the surface of the site. In collaboration with RIMARE, an associate research unit about mass movement and hazard assessment and risk evaluation in Lebanon, an experimental characterization of the site was performed, and it consisted of a geotechnical investigation and a geophysical investigation, as we can see in this figure. This is the Pan-Arab Highway, the under construction road. This is a failure line in the slope. And those are the boreholes and the geotechnical investigations. And here we have the geophysical investigation, MASW and ERT, that we will talk about later. And the geotechnical investigation, it included drilling 8 different boreholes, as we saw on this photo. It included in situ testing as well as laboratory testing in order to collect all the necessary information needed for the slope study. After carrying out all the soil investigation, many sections were established. In this study, we will present only the section EE. We can see that the different soil formation from the fill material here, which is composed of marl and clay, the clay sand, marl and sandstone. We can note that the water level detected with piezometer during the investigation is deep. From this investigation, we collected also the soil properties, which we can see in this table. Now to the geophysical investigation. In this geophysical investigation, 3 types of tests were conducted, which are the MASW, multi-channel analysis of surface waves, the H/V, which is the HVSR technique, and there is resistivity test. Let's begin with the MASW. This method is a seismic exploration method, evaluating ground stiffness for various types of geotechnical engineering projects. It analyzes the propagation waves, velocities of these surface waves, and finally deduces the shear wave velocity and the compression wave velocity. After all the calculation steps for these 2 profiles that I'm showing now, we had the profiles of the compression wave velocities and the shear wave velocities on the side. As we saw, the profiles that they are that they correspond to the soil encountered in the site, and specifically for section in the section E. So as we can see here, we deducted the shear wave velocities and the compression wave velocity for all the different layers in the section EE that we will use later in stability analysis. Let's pass to the H/V tests. This method is frequently utilized to rapidly estimate the natural frequency of a soil as well as the depth of the bedrock. As we can see here, the dominant natural frequency was detected to be between 3 and 5 hertz. And through this equation, knowing the F0 and knowing the depth of the soft soil, we deducted the values of also the values of the shear wave velocities. The tests showed a wide range of values for the shear wave velocities, which confirmed the variability of the soil layers and parameters and the Dahr-Baydar slope stability. Now for the ERT tests, 2 different profiles were performed. The electrical resistivity tomography that we call ERT. We did the 2 profiles on the site, and it showed this is the first profile, which is the upper profile in here. It shows 2 zones mainly. One zone with high resistivity, which represents the sandstone formation, and the second zone with low resistivity and represents the clay and marl layers. As well as in the profile 2, we had 3 different zones of resistivity. All the information that we had in the geophysical investigation were very conform to the geotechnical investigation, as we can see in the soil layers and resistivity and the shear wave velocities for the soils. After the data collection and the interpretation from the geological, geotechnical, and geophysical investigations, slope stability study of the Harel-Baidar slope is launched, and in particular for the section EE. At first, for the static analysis, it was done on the software Talran4 by TerraSol and Plaxis 2D. The soil parameters that I showed earlier were used in the softwares. Talran4 is a slope stability program that uses classical moment equilibrium to evaluate stability of the failure surfaces. This result shows that a factor of safety of 2.68 of the slope was calculated. To note that the water level here that we used is the one recorded in the piezometers at the time of the investigations, which is low. And the same section was studied on Plaxis 2D, which is based on Moore-Coulomb model material for the soil behavior. And the factor of safety is calculated using a phi-C reduction calculation. We can see that we have very similar failure surfaces and very similar factors of safety. But as the static stability studies has shown a stability in the slopes with no failure, which does not represent the state of the slope at the moment of the landslide. Therefore, further dynamic analysis was performed to evaluate the slope failure under earthquake loading. This dynamic stability was performed on Plaxis 2D and using the compression and shear wave velocity from the geophysical tests, which are represented in this table. A velocity signal is used to introduce the dynamic condition in the soil. This was a recorded, an actual recorded signal in Lebanon. And this dynamic calculation phase 8 point were chosen on the surface of the slope and on the interfaces between the layers, the soil layers. As we can see, the output velocity spectrums right now for the 8 points were deducted from Plaxis 2D. And as a conclusion, as a general conclusion for this these results, we can see that the amplitude of the point A in the spectrum, this one was the highest among all the others. The highest peaks noted in the spectrum corresponds to a frequency around the 3.8 Hertz, which matches well with the natural frequency in the ground. And the point H spectrum is similar to the input signal spectrum, which is normal as the point H is situated on the bedrock. After comparing all the spectrums of the surface points, which are A, B, and C, in horizontal direction with the input signal spectrum, it is found that we have an important amplification between 2 and 10 Hertz, as we can see here for the point A. And as a general conclusion, we can say that the layers with an amplification in their spectrum are actually the layers that are situated on and above the failure surface and that are subjected to failure as observed in the static model results. As a conclusion, since the static analysis showed a stability with a high safety factor when we used a deep water level, and since the analysis of the soil data has shown a high fine percent, especially in the surface layers, and since the fine soils lose an important part of their cohesion in the presence of water, and After a surface water infiltration was detected on site during only particular seasons, and after the dynamic analysis has shown an amplification in the spectrum of the upper surface layer situated on and above the failure surface, it was suspected that the failure has most probably occurred at the interface between the soils with different rigidities or within the soft layers themselves. The failure occurred during the season of water infiltration, where the water seepage has induced an instability in the slope due to a buildup in pore water pressure and to the increase in soil weight. And we suspected that the seismic activity of the surrounding faults may have triggered also the slope instability. Additional studies are needed to be able to further investigate the slope failure causes, which are geotechnical and geophysical tests for a better characterization of the site. A detailed hydrogeological investigation and study is needed also for the site and its surrounding, and as well as a study for pore water pressure in different seasons. The seismic activity of the site and the surrounding faults must be traced and studied further, and supplementary slope stability analysis is required after all those studies to be able to know the triggering causes of the slope instability of Dahr al-Baydar. Thank you for your attention.
Thank you, Sabina. It was a nice overview of wide spectrum of investigation and analysis, and we can go to the last presentation. Professor Diana Salchiarini will have a presentation of physical and numerical modeling of the response of slopes under different rainfall inclinations and vegetation conditions. Please.
Yes, can you see my screen?
Yes, yes.
Okay, thank you, Mr. Chairman, for introducing my talk today. I would like to acknowledge the contribution of my co-authors, Renato Morbidelli, Elisabetta Cattoni, and Evelina Volpe from the University of Perugia, eCampus University, and National Research Council. I'm going to present some summary of the results that we obtained from a physical and numerical investigation on a slope after different geometrical configuration and boundary conditions. As we well know, many variables affect the stress-strain condition within this slope and thus its stability condition in a variable manner depending on the water infiltration process, which is ruled by many factors. Above all, rainfall rate, which is an hydraulic aspect, inclination, which has an impact on soil permeability, and the presence or absence of vegetation, which has an impact both on soil permeability and on mechanical characteristics. So the goal of this work is to find some insights on the response of a slope considering all the variables listed so far: rainfalls, slope inclination, and presence of vegetation. This is a brief outline of the talk. I will show the experimental setup. I will describe the experimental finding and some numerical results obtained by a finite element analysis. As for the experimental setup, a small-scale artificial slope was implemented, and rainfall was applied by means of a rainfall simulator devices that was designed to provide a steady and uniform rainfall, and it is placed directly above the slope and linked to a supply and distribution system. Other basic components of the experimental setting consist of hydraulic network and hydrologic measuring equipment to control the inflow and outflow process, a data acquisition system, and a high-resolution camera to record the stability evolution. The small-scale slope, as you can see, is made of a galvanized steel box with a plexiglass side wall for the complete observation of the mechanical phenomena that occur. And the box can have different inclinations controlled by hydraulic pistons at the bases. Here, the small scale slope is represented in its final configuration used for the analysis, with a maximum inclination of 30 degrees and a local modification of the geometry in the low part of the topographical surface to simulate the presence of an excavation work. This is a sketch of the experimental setup. The box is filled with 2 layers of soil. The upper soil is basically a sandy soil. The lower layer is a silty sand. Here you can see in the graph the grain size distribution curves for the soils. And we perform some simple shear tests on the upper soil, and we identify the soil as a purely frictional soil with null cohesion and a friction angle equal to 29 degrees. As for the experimental tests, they can be subdivided into 3 groups. The first one was devoted to study the effect of the inclinations. The second one was devoted to study the effect of rainfalls on the bare slope. And the third one was devoted to study the effect of vegetation. As for the group A of tests, we tried to quantify the effect of steepness on the surface flow, and thus the experiments have been carried out considering different types of inclinations, starting to 10 degrees up to 26 degrees, under the action of a heavy rainfall. As you can see from the table, the average rainfall rate was about 60 millimeters per hour. Surface and deep flows were monitored, and the graphs show the evolution of the surface and deep flow in time for the 4 tests performed at different inclination. This graph shows that as the slope inclination increases, the steady surface flow increases, and consistently the steady deep flow decreases. And we could find a relation between the steady surface flow, the steady deep flow, and the inclination under the same rainfall intensity. As for the results of the second group of tests, in this case, we kept constant the artificial slope inclination to the maximum value equal to 30 degrees. And we realized a local inclination of 60 degrees, simulating an excavation work in the lower part of the artificial slope. We test 2 patterns of rainfalls. The first one is a low rate rainfall with an intensity equal to 15 millimeters per hour. And the second one is a high rate rainfall with 60 millimeters per hour. We observed no failure for the low rate rainfall, and we observed failure as shown in the picture after 4.55 hours of rainfall for the high rate rainfall. Also, it is interesting to observe that prolonging this rainfall up to 10 hours, we observe no other failure in the artificial slope, nor erosion mechanism, except for the one located at the excavation work, despite the quite high global inclination. As for the results of the third group of tests, of experimental tests, we saw green grass on the artificial slope surface, and we repeated the test using the same rainfall pattern. In this case, the research was focused only on the mechanical improvement due to the vegetation, and we neglected the hydrological aspects. At the end of the experiments, no instability nor superficial erosion occurred, demonstrating in a qualitative manner the beneficial effect exerted by the route. And we would like to investigate deeper this aspect. So to better understand the effect played by the vegetation, we built up a 2D finite element model of this small scale equipment by means of the use of the GeoStudio suite. And in particular, we use the SIP-W code to perform transient finite element seepage analysis, and the slope W code to perform slope stability analysis at different times during the transient infiltration process, with the aim of reproducing the infiltration process and the stability mechanism observed in the lab, in the experimental test in the lab, both considering the bare surface and the vegetated surface for the slope. As for the hydraulic parameter of the model, we use the results of the previous experimental test performed. As for the case of bare slope, we use a purely frictional soil with friction angle equal to 29 degrees. As for the case of vegetated slope, we performed a back analysis to estimate the cohesive contribute introduced by the roots, neglecting the additional beneficial effects of the hydrological type. As for the rainfall patterns adopted, we use the potential sepal phase boundary condition available in the SIP code. Coming to the results, as for the bare slope, we test the numerical model with the two rainfall pattern. We obtain a stable condition for the low rate rainfall, and we obtain an unstable condition for the high rate rainfall as observed in the experimental test, demonstrated by safety factor less than 1. As for the vegetated slope analysis, we performed a back analysis imposing the safety factor equal to 1 for rainfall event with a rainfall rate equal to 60 millimeters per hour, and using the transient infiltration results at the failure time observed during the experimental test. The back analysis demonstrated that to obtain the limiting equilibrium condition, meaning safety factor equal to 1, the value of 10 kPa need to be adopted for the soil, for the tested soil, obtaining an increment of 12% on the stability condition with respect to the bare slope. I would like to underline that and repeat that only the mechanical effect of the vegetation is considered in the analysis, neglecting the hydrological benefits. So coming to the conclusion, we observe that the inclination of the topographical surface plays a role in the infiltration process, with an infiltration into the subsoil that decreases as the slope increases in approximately linear manner. The bare slope was monitored with the aim of recording the instant of failure. Then a grass carpet was sown on the surface, and the evolution of the slope was monitoring, and the beneficial effect of the root was qualitatively observed. And finally, we tried to quantitatively estimate the beneficial effect exerted by the root with a numerical model taking into account the mechanical improvement. Thank you for your attention.
Thank you for nice presentation. We just carry out similar investigation in our laboratory, and it was fine to see similar results. Thank you another one time. And we can go to the invited lecture. Gravitational movements in the stiff clays of Sinard Plateau, Western Arms, monitoring kinematics and rheology, will be presented by Professor Dennis JONGMANS. Professor JONGMANS is full professor in applied geophysics at the University of Grenoble, France, and the main fields of his investigation are development and application of geophysics methods for landslide investigation and monitoring. Please, Professor JONGMANS.
So thank you, Professor Banas. Do you see my slide?
Yes,
okay. So good morning, everybody, and thank you for inviting me in this first Mediterranean symposium on landslide. So my talk will be about the gravitational movement in the stiff clay of the Sinard plateau. It's in the French Alps, with a focus on kinematics and rheology. So I will leave my field of applied geophysics to go more into geotechnical engineering. So as we have seen this morning, the landslides in clay-rich formation pose serious problems for population facilities, because first they are widely spread in the world, but also because they may affect both upstream and downstream zone by retrogression of the headscarp, shown by this blue arrow, or the propagation of the toe, shown by the red arrow, especially if the material shows a fluid-like behavior at this toe with different mechanism, and Matteo Berti discussed this point this morning. So the questions that we would like to address is...
Professor JONGMANS, can you enlarge your presentation because we can see...
Sorry. No, it's not. Oh, yes, it's... okay, I see the problem. How can I... Sorry. So I'm going to leave it and to come back. So.
Okay, thank you.
I'm sorry, I cannot find where to change. It's here. Very sorry, I do not see how to stop that.
Professor JONGMANS, you can see answers in chat. How to
do you see it now?
Now it's okay. Thank you.
It's okay. Okay. Thank you. Sorry for this disturbance. So I was at the third slides, I think. Yeah. Okay. So there are two main mechanisms proposed for explaining the flow-like behavior in clay-rich landslides. The first one is the elastoplastic approach, usually for water content lower than the liquid limit, so in the plastic state, where the main phenomenon is increase in pore water pressure, generating acceleration and displacement. It was shown by different authors this morning and probably yesterday. And I just show an example of that, which was given by Iverson and Major in 1987 for the Minor Creek landslide. And the main movement type in clay, of course, for that is flow. But there's another option, it's one-phase viscoplastic approach, when the material is a yield stress-free behavior. It was shown here on the right by creep tests with a rheometer on the Montevecchio clay, so the garden of Matteo Berti. So what you see here is an evolution of the shear rate strain as a function of time. And what we see is that when we increase the shear stress at a given stress, you have a fluid-like movement with an apparent viscosity over this critical stress, which is in this case, it's around 168 Pascal. And the point is that sometimes this evolution is gradual and sometimes it's very abrupt, like you see here for this Montevecchio clay. And in this case, we speak about a viscosity bifurcation in viscosity, which shows the thixotropic behavior of the clay. And the classical movement type associated with that is a fluid behavior, which can be described as mud flow or as the fluid earth flow as described this morning. So the aim of this talk is to try to understand a little more from field observation, this earth flow and mud flow, and we looked at a site located 30 kilometers south of Grenoble, which has been affected by both earth flow and mud flows. So it is located at the limit of the glacier during the warm period here, as you show in white, and this glacier blocked the valley and creating a huge lake of 300 square kilometers. And this lake was filled with thick laminated clay deposits with a thickness which can reach 250 meters. And as the site is just at the limit of the glacier, these clays are over-consolidated by the weight of the glacier, which can reach a few hundred meters. So this is the context for the geology is shown here with a geological map and a geological cross-section. So from top to bottom, we have moraine cover, can reach a few tens of meters, with this laminated clays in gray here, overlying mostly a substratum made of marls and limestone, so Mesozoic age, and the landslides developed in this clay and sometimes affect the morainic cover. An important point is that we have a lake here, which is not the Paleo Lake, it's a man-made lake, which was built in 1961 and which is located at the toe of the landslide. So here's the landslide shown by LiDAR image taken in 2016. And so it has a length of about 1.5 kilometers with a mean slope of 9 degrees. The total volume was estimated to 45 million of cubic meter. And so there was a more active zones in the central part, as you can see here. And the morphology is clearly different at the top and at the toe. In the upper part, you have some concave shaped scarps, which can reach 30 meters high with rugged and bare topography, while in the lower part is characterized by convex ridges. So you see the zoom on the lower part of the landslide, and you see these very nice ridges here with a smoother topography and dense and thorny vegetation. So this landslide was reactivated in 2016. And so that gave us the opportunity to study it in more detail. And so just to show you a panoramic view and to show you some pictures of this landslide. So here from north to south, so you have the headscarp with this blocky part with this very rugged topography, with blocked of clays that have slid in the landslide. You have sack ponds here, a secondary scarp here at the limit of the continuous vegetation, and over this secondary scarp, you see that you have the vegetated area and the lake, so the artificial lake to the south. So now, if we look more in details, oh yes, I have forgotten to mention that this is a compound slide in the upper part because we have some rotational component, you will show, but we have also some horst and graben features that can be distinguished here in this part. So if we look into more detail, so here is the main scarp. At that site, it makes 25 meters, and you see with this very stiff clay, which are really soft rock at this state, and you saw the motion with a rotation of the block of clays sliding along a slip surface. And just after the landslide, it was possible to observe some linear stride showing that the motion was really a rigid motion with friction. an interesting point that if we look inside the landslides, we can find this laminated clays, so that you see here, but also another type of material made of unlaminated clays with pebbles. You may very well see the pebbles here. And this second material is probably generated by the glacier. We say some episodes of advance and retreat, and which has eroded the sediment into the lake and has deposited this material, this heterogeneous material. So we find the 7 layers, of course, of this material. If we are going down, you see the 3 stars, red, orange, and yellow. And I will show you some pictures at these sites. So the first one here is for the red stars. We are maybe 300 meters from the headscarp, and you see very well that the topography is smoother, that the block have been eroded and weathered, and they look more like mounds here. And you see very well these pebbles. If we go a little down in the landslide, you download in the landslide. Here we are in the vegetated areas, and with the presence of some scarps and some bulges. And this topography makes the ridges that I showed you on the LiDAR. And finally, the yellow star, which is at the tower of the landslide, and the contact with the lake. At that point, the material is flowing into the lake, and we are over the liquid limit in this zone. But of course, we are in the beating zone of the lake. So what we try to do is to perform a multi-method investigation of this landslides, combining field observation, geophysics, remote sensing, UAV and image processing, and geotechnical tests. So very briefly, so we studied the seismic rupture precursors at the headscarp, instrumenting a block before that it slides, and showing that with seismic noise, that it was possible to obtain some precursory patterns on some parameters like the variation in velocity or the correlation coefficient using the correlation technique, and also on the number of events or the resonance frequency. So it was a paper published in 2020. We also studied the structure of the landslide using some geophysical techniques. Here is so also the seismic noise, and we made some surface wave inversion from this noise. And we were able to locate the slip surfaces, which we are shown by contrast in shear wave velocity. And in the upper part, as the blocks, where the blocks are slid inside in the landslides, very quickly they are weathered, and so we try to understand and to study this degradation of the clay of the clay blocks. And so we studied this by using UAV photos and computing an evolution of using the classification of the material, and computing the evolution of the surfaces of the different materials with time over a period of 2 years. And with the roughness, we were able to show a very high degradation rate of the clay materials in this zone. We also used some satellites and optical satellites and LiDAR airborne data in order to study the mass transfer during the 2016 event from the top to the toe. I will show you the results in a few slides. And finally, we tried to obtain some mechanical properties inside and outside the landslides in order to understand better the mechanism. So let's start with the chronology of this landslide. And here you have 6 aerial photos from 1948 to 2016. And during the first stage between 48 and 81, there was just slope erosion in the gullies, as you can see here in blue. In 1981, there was a main event with a massive landslide of a few millions of cubic meters, with a retrogression of from the erosion zone, the top of the erosion zone, to a main headscarp. Between 91 and 2016, there was a discontinuous retrogression of the landslide, of the headscarp of the landslide, with an average of 5 meters per year. That was shown in the orange rectangle. And finally, in June 2016, a major reactivation occurred at the headscarp, and I will give you the characteristics of this landslide a little further. So here's a topographic profiles showing with the same color the retrogression of the headscarp with time. So if we compare the main two events, the one in 1981 and the 2016, a major differences is a retrogression area. It was much more important in 1981 than in 2016. If we look at the pictures taken just after the landslide in 1981, so you have the scale with the people here looking at the landslide. You see that it was during during rainfalls. That was a rainy period. You see the water here just below the headscarp, which was around 20 to 25 meters high. And here below you have infrared in aerial photos showing the landslide and the flows of the material into the lake. So it was interpreted at that time as a mud flow. The 2016 event is different. It occurred in dry conditions. And you see the picture with sunny conditions. What we did is that we use a LiDAR and optical satellite data in order to track the mass transfer from the headscarp to the toe. And here to the right, you have 5 drawings showing the moving of this mass, and it is shown by elevation differences. So in red, you have negative elevation differences that we erode, and in green, you have positive elevation differences we deposit. And so you see that from here we are in June, and at the end we are in the beginning of August. So you see that in 5 weeks from one picture to the other, you see the mass transfer of through the subsurfaces. You see the mass transfer from the top to the toe of this landslide, and the mass was about 1 million of cubic meters. So it was a very quick transfer, allowing to keep the headscarp free of material in front of it. So if we compare the two events, so first in terms of weather conditions, so it's here at the bottom you have the mean temperature, the daily precipitation, and the snow height. So there was some snow in 1981. From testimony, there was 30 centimeters of snow. Well, at the meteorological station, which is a few kilometers from the site, it's less, but of course, as everybody knows, it can change very, very strongly. But there was some snow, and so there was a warming in temperature, as you can see in the red curve here. And so the rain contributed to the snow melting, and so to the infiltration of a relatively high quantity of water. While in 2016, the weather conditions were dry, as you can see here. During the 10 days before the landslide, there was no rainfall. There was some rainfalls before, of course, but not during the landslide itself. The runout time is less than 1 day from testimony again during 1981. It was very quick. So here the mass transfer was in 5 weeks, as I showed you, with a volume displaced in 2016 that was 1 million of cubic meters, while in 1981 it was not known, of course, at that time, but we we constructed the new DEMs from the aerial photos, and so we were able to bracket it, and it's more, it's close to 3 million cubic meters. And the mechanism at the top, of course, it is a fluid behavior, of course, in 1981, so it was interpreted as mud flow, while in 2016, it's clearly earth flow with multiple slip surfaces. So there was absolutely no geotechnical tests made in this landslide. There was some tests in the area, in the Sinard plateau, but not at that site. And so we tried to perform at the end of a PhD thesis some geotechnical tests in order to better characterize the material and to try to understand why we have this difference between 1981 and 2016. And so what we perform is 3 dynamic penetration tests, P1 to P3 here, below the escarp to characterize the parent material with 1 borehole. We took samples, 9 samples from the escarp to the tow for identification tests, and we performed 2 triaxial tests at S1 here, so behind the escarp, and at S7, so which is in here in the discharge zone, and 3 radiometric tests, S1, S2, and S7 sites. So first, the results of the in situ test, so the penetration test. So here to the right, you have the geological log showing the stratigraphy with the morainic colluvium, the weathered clay, and the laminated clays in gray. You have the resistance profile showing for the black line, it is a P2 located far from the escarp, 250 meters. So you see here clearly a good match with the soil stratigraphy, with a more resistance layer for the morainic cover, a decrease in resistance, and then an increase with depth in the laminated clays. And what is striking is a difference between the resistance profile at P2 and P1. Of course, at P1, you see that we have some dramatic drop in strength inside the weathered clay that we observe also in P3. For simplicity, I did not have this information, but we have the same kind of results. So very low, very soft zones, which can reach, you see here, almost 1 meter in this weathered clay. And this was completely new and unknown at this site. So we also performed some laboratory tests. And so, as you have noticed, we performed a very few number of tests, 2 and 3 for the mechanical tests. And so we measured them, the characteristics in the weathered laminated clays at the escarp and in the degraded material inside the landslides. And we compared this result to the one found in the literature. So here I just present a very, I summarize the main results of the geotechnical test here with the different parameters at the escarp, in the landslide, and compare with the literature. For the 2 parameters where we have 9 measurements, what we observe is that we have an increase in the liquid limit inside the landslide, which is quite obvious. You see that the range of the measurements we make are in the range which was found in the literature for the area. The percentage of fines decreases dramatically from the escarp to the landslide, and it was not seen in the literature before. The literature gave value between 20 and 40 in agreement, which was found at the escarp. And for the porosity, we have a slight increase of porosity from the escarp to the landslide, but we only have 2 measurements. And for the mechanical properties, I'm going to detail them in the following slides. So for the triaxial test that we performed from samples in the stable zone, so the escarp and the landslide, so we have the comparison between the 2. The striking result is that we have a decrease in cohesion from 54 to 8 kilopascal, maybe with a slight increase in the friction angle. And of course, it's only 2 results, so we try to have more confidence in our results, looking at what was observed in the literature and on other landslides, and where we are sure that the tests were made on material in the landslides. And so we found 2 landslides, the Avignon landslide, which is very close to the Armalière one, and the Possonas landslide. And the authors found some very low cohesion values in agreement with what we found, and friction angle which are close also, they are close to the ones that we found. So we have a little more confidence to our results. So we show a low cohesion in the landslides with a friction angle around 22 degrees, and a decrease in cohesion from the stable zone to the landslides. I remind you that the 54 is for the weathered clay. Of course, it's the laminated clays, in the sound laminated clays, the cohesion is much higher. And concerning now the radiometric test, so we were able to compare our result with the result found in the literature for exactly the same area. So in this study, you can compare the radiometric profiles, so the creep test made in the stable zone, so over the liquid limit, in the stable zone and in the landslide, and you see there's a difference in shape, which is quite visible. In the stable zone, we have thixotropic behavior with a bifurcation of viscosity that is shown here, which is not clearly visible inside the landslide, where we have a more regular evolution with a shear stress before obtaining this critical shear strain rate, where the material becomes liquid, with an apparent viscosity which is lower in the stable zone, because we have a shear strain, higher shear strain rate, and which is higher, sorry, in the landslide. And if we compare now with the previous study, so we found 2 previous studies made in the same area, in the stable zone and in the landslide, and you see that the authors found some similar results in terms of shape and in values. And so that gives us confidence in our results, so that which are the following: that in the stable zone we have a marked viscosity bifurcation, meaning thixotropy of the clay in the stable zone. So in the laminated clay with a low apparent viscosity of this value, which corresponds to this line, to this shear strain rate, the critical strain rate. In the landslide zone, we have a higher viscosity, which is shown here by the dashed blue line, with no thixotropy. And so the presence of the thixotropic clays, of course, with this very rapid change in behavior from solid to fluid, is consistent with the soft zones that we may have in the penetration that you may find with the penetration test. So sorry, that's my phone ringing, but it will stop. And so if we look at the influence of this geotechnical test on the landslide mechanism, so what we obtained is that the percentage of finds decreases inside the landslides, and our interpretation that is probably due to the mixings of the 2 materials that I showed you, and the consequence is the increase in liquid limit in the friction angle and in the apparent viscosity, that the porosity increases inside the landslide caused by the degradation of the clay that was observed in other landslide all over the world, and it gives, of course, the possibility to increase the water content. The cohesion decreases for the same reasons, for the degradation of the clay. It's our interpretation. Of course, the decrease in cohesion favors the multiple slip surfaces, especially so creating some earth flow. And the apparent viscosity increases in the landslide, probably because, again, of the mixing of the material, while the bifurcation of viscosity decreases, or the thixotropic characteristic decrease with inside the landslides. And so the consequence that at the tau here, we have mainly earth flow. That was what was observed. We have exceptionally, we may have mud flow like the 1981 event. And at the top, in contrast, the thixotropy of the clay may favor the instability and retrogression of the escarp. So I have a little sketch here showing that when you have some fracture here behind the escarp, which is here, so rear fracture, which are open in the morainic cover. So you may have infiltration of water, and that means that we may reach the critical stress here at some point and cause a liquefaction, a fluidization, more exactly, of the clay, which favors the instability of the escarp. So my conclusions are the following: that at the escarp, so in the source zones, we have a compound slide with a quick degradation of the material and a fast transfer of the mass to the toe, so making free the space in front of the escarp. The clay, it's thixotropic at the escarp with development of soft zone along fractures, and so it's contribute to the permanent instability of the escarp. And these two factors explain the quick retrogression of the escarp and the continuous refreshing that has been observed for now 60 years. And a major consequence of this is that you see on this aerial photos the first houses, which are located here, maybe 200 meters or less than 200 meters from the escarp. And then from the retrogression rate, the first houses will be or should be effective in 30 years. So it's relatively rapid. And the second set of conclusion concerning the lower part of the landslide. So we have an increase in porosity, a drop in cohesion, and no viscosity bifurcation. So that explains that the main mechanism is earth flow with slip surfaces, with deformation located on slip surfaces in this lower part. And it's just in very specific conditions where we have some heavy rainfalls with snow and a large mass which is mobilized in the source zone, that we may have some fluidization of the degraded clay. So these results have to be confirmed by additional geotechnical tests and also with modeling, not only for science, but also for the tourism development in this area. So thank you for your attention.
Thank you, Professor JONGMANS. Very nice presentation, very nice data and analysis. So we conclude the presentation in this session, and we can start with discussion. I am now I'm calling audience to address their answers to all lecturers that have presentation today: Professor Alonso, Professor Berti, Professor Essa Di Maio, all speakers, and Professor JONGMANS. We have about half an hour. I am opening chat, and here I can see only one question now. Maybe...
Sorry, Professor. Yes. I have a communication to participants. If someone wants to ask live questions, he can write it in chat so that the organizer can activate webcam and microphone. Thank you.
Thank you.
Okay.
So I can see only one question now in chat. It is maybe the first question by Professor Piccarelli to Professor Berti. Professor Berti, can you open chat and you can see question here? It is better that you read it in the chat than to listen me. Professor Berti, do you hear me? No answer from Professor Berti.
If you want, I may ask a question to start.
Yes, please.
Yes, another speaker. So I have a question for Stefano Morelli. Do you hear me?
Yeah.
Yeah. So thank you for making our study live with your work. And so effectively, there are still some pending questions and about the use of geophysical imaging and geotechnics. And so in France, we have the feeling that there's a loss of interest in applied geophysics, and it's relatively evident and distrust as well. And so I would like to know if it is the same in Italy.
Yes, really, it's the same. There is a very high interest in these techniques. The problem is to convince, how can I say, to sell the importance to the users. Yeah. Because from one side there is the academic part that is interested and is now working, but from the other side, professional, until now they want to use the traditional methods because they are more confident with this. So the next step is to convince them to use these techniques. So there is two parts.
Yes, the paradox is that the techniques have dramatically improved the 20 years, and we found in France that there's a loss of interest in this technique. So it's quite amazing, and I don't know what to do with that.
Yes, we have to increase the interest, the application. Yeah.
So thank you.
Thank you.
Thank you. Other questions? No other question for now. I have a question for
Professor Arbanas. Sorry, yes. Professor Berti writes that he cannot see the question of Professor Picarelli. So could you read the question, please?
Can I share the screen? Yes.
Okay, thank you. Thank you so much.
Can you see the screen now? First question.
Yes, but if you want, I can read to Berti.
Yes, okay.
The question. Okay.
The concept of phase transition is an intrigue one, but naturally it misses reality. The point, I believe, is in the strong change that takes place in the interparticle interactions. Professor Betty, you can answer live or type your answer here.
He wrote that he cannot enter the microphone.
Yes.
Okay, can you hear me now?
Yes.
Oh, sorry. Sorry,
okay.
I was logged in as a guest, so I couldn't answer. So sorry for the delay. Where is the question? I can see your screen. Where is the Luciano question? I cannot see the question now.
Matteo, the question was asked at 11:50, so you have to go a little up in the list.
Okay, 11:15.
Is it the first one? Is it the first one?
The first question from Luciano.
I'm sorry. Sorry, I cannot see any list of the question. I'm surfing.
Do you want me to read it?
Yes, thank you, Dennis. Thank you.
Yeah, so the concept of phase transition is an intriguing one, but naturally it misses reality. The point, I believe, is in the strong change that takes place in the interparticle interactions.
The point is, sorry again?
The point, I believe, is in the strong change that takes place in the interparticle interactions.
Well, okay, I know that, yeah, I understand this point. And also yesterday, many authors underlined the importance of let's say, particle contacts and the presence of discontinuities and so on. And I strongly believe that let's say, the geotechnical characteristics and so the context between the clay particles, the clay scales and the discontinuities, all this stuff is of course of paramount importance, but this is just my idea now, especially during the relatively, let's say, slow movement during the dormant stage or maybe the accelerated dormant stage. But the point is that, I mean, my focus was in the talk on the rapid stage of movement, which is something very particular that happened in a very short time. And so in that stage, the impression when you go to the field immediately after this kind of rapid movement or mud flow, as you call them, Dennis. So in case of a mud flow, the impression is that the material is not solid anymore. Mm-hmm. So it should be, it's really more like a fluid, and probably, and so the water content is so high, probably higher than the liquid limit. So probably we are not working with soil mechanics anymore, but with fluid mechanics probably. So the geotechnical concept and for example, the interaction between particles are maybe not so fundamental in this very particular stage. I don't know if I answered Luciano's question.
Professor Piccarelli, can you hear your comment? Can you give your comment, please? We cannot hear you.
But the microphone is open.
Yes.
Professor Piccarelli.
Okay, maybe we can go away. Here we have another two questions for Professor Alonso. Professor Alonso, can you hear us?
A second, can you hear me?
Yes, yes, yes.
Okay, if you, I think the best thing is if you can read the question and then I will try to answer.
Yes, the first question is, did you take account of Poisson ratio in the evaluation of change of length of penstock? It is a question from Alessandro Jaio.
I think he refers to the, can you read it again?
Did you take account of Poisson ratio in evaluation of change of length of penstock?
Oh yeah, I mean, the penstock was, the model was an elastic model, was a steel, so it was characterized as an elastic material, yeah.
And the second question is from Gianfranco Uccioli. I found very interesting the non-linearity of shear strength envelope. Can you justify this phenomenon?
Well, this is very typical, as you know, of rock joints in which you have some roughness. Mm-hmm. So the roughness provides, in the interpretation typical in rock mechanics, this non-linearity. And in fact, in some of the pictures that I've shown, you can see this roughness in this contact surface between the claystone and the sandstone banks. And I think this is the reason. The reason is this roughness. In fact, we well, something that we did, I couldn't mention, is that we took, after the test, profiles in detail of the surface, of the shearing surfaces. And we analyzed those profiles using techniques of rock mechanics. For instance, for instance, the Barton type of approach to derive the strength envelopes on the basis of the roughness of the profile and some other parameters, and we compare that with the actual measurement. So yeah, I will say that the roughness is the key information there.
The roughness is the reason for this nonlinearity.
That's right.
Someone start to write another one question, but it is not appeared yet. Any other question or any comment to Professor Alonso back? Not yet. Okay, I have a question for Lorenzo. I think it is very fine presentation about triaxial investigation of this kind of material, and I think it can be a problem with the scale, the problem of the grains that can be used in this specimens. Did you consider how to use this for different types of this material with bigger grains in matrix? Do you consider something about similarity laws that can be used, and then you can apply these results to some other materials? It can be very interesting.
Yes, can you hear me? Because I cannot switch on my webcam. I can only...
Yes, I can hear you.
Okay. So if I understood well, the question is divided in two parts. First of all, yes, the dimensions of the rock blocks are an important point in this study, and to prepare the specimens, we followed some suggestion from many authors which carried out previous studies about the minimum and maximum limits of the dimensions of the rock blocks, which actually influence the mechanical behavior of the heterogeneous material. And these dimensions were basically the minimum limit was the 5% of the characteristic dimension of the problem, which in this case was the diameter of the specimen, and the maximum limit was the 75%. Then we had to reduce the maximum dimension to reach a compromise. We wanted blocks big enough to let's say give a variability in the grain size distribution, but small enough to avoid executive problems like I showed before, the problems in the extrusion of the specimens. And with bigger blocks, there is the risk of destroying the specimen, which cannot stand on its own weight without collapsing. So we had to reach this compromise. Then we want to extend this study, and we will find a way to extend the investigation with different grain size distributions and different dimensions, specifically to extend the field of applicability of this study. We have to then consider all the dimensions and also the shapes and the orientations of these blocks. In this first experimentation, the blocks were with variable shapes, but more or less spherical. There were not very flat or let's say ellipsoidal blocks with a big eccentricity. So I don't know if I answered your question or not, but we will extend this study with many different shapes and dimensions of the blocks.
Okay, thank you. And another one question. I had many problems with similar materials in my engineering practice, and for this kind of material, we used Marinos and Hook's proposal for shear strength envelope. Did you ever try to compare your results with results that can be determined for this empirical proposal?
Yes, we didn't do that yet, but we will do it. The starting point of this study was that we wanted to check to find similar relationships valid for our BIMROC, which is quite different for the others because it's a transition material between BIMROCs and BIM soil because the matrix is either very over-consolidated soil or a very soft rock. So it's a particular kind of BIMROC, but we will do that, and we didn't do that yet.
Okay, thank you. I will follow your research, and I hope.
Okay, thank you.
Good results. Thank you. Any other question?
May make question to Professor Alonso and Paolo Tommasi.
Yes, please.
Oh, thank you. Professor Alonso, good morning. And thank you for your very interesting presentation, for your very interesting data on shear strength of joints. I would like in this respect a couple of detail about the interpretation of the in situ shear tests. First, did you find steps along the shear discontinuities in the shear surfaces that can justify very steep part at low normal stresses? This is first. The second is, did you try to enucleate, to divide the contribution of the roughness and of the base friction angle by back analyzing the shear tests with the Barton model and by measuring roughness directly on shear surfaces? Thank you very much.
Yes. Can you hear me?
Yes.
All right. Perfect. So I just start with the second question. I think I mentioned something about that. That's right. This is what we tried to do. So we had those 6 big samples, and then after the test, we simply open the surface so we can study it in detail, and then we actually plotted I think 3 profiles or around 3 profiles for every sample in the direction of the shearing, and then we used the ideas of Barton in order to derive and strength envelope on the basis of this information, plus, for instance, the let's call it basic friction angle. I didn't want to call it a critical state or residual, but okay. So yeah, basic friction angle plus normal stress also goes into the expression of Barton, and I don't know if something else, but this is, I think, the main components. The problem was that it was very difficult to identify the roughness as the typical roughness is published by Barton. If we try to compare that with the real one that we actually measure, why? Because in some of those profiles, we suddenly found some ridge there, and then some relatively planar surface, and another ridge, and that's it. Not just a random kind of a random surface there, with relatively, some correlation in these profiles. No, I mean, it was a different story. And this was the major difficulty. And probably this explains something that you said is why you get some increase at the beginning, in the strength when you have a small displacements, etc. You always tend to find that, but out of the 6 tests that we performed, we found very different results. However, of course, geologically speaking, it was the same type of contact, and however, there were major differences, and this has to be related to local changes in the geometry of which was complicated, difficult to define, of the shearing surface. Okay, the surface that actually we use to apply the normal and shear stress. So you at the end of this exercise, well, you come to the story that probably of course, a representative shear test should be bigger in size, but this is almost impossible. I think the biggest that I know is around something like 4 meters by 1 meter or 4 by 2 meters, which is a major, involvement in performing this type of shear test. And then you don't know what to do, when you have these variations. So yeah, I don't have a nice answer. In the work of Barton, there is Barton and something, I don't know somebody else, but there is some attempt to correct the strength on the basis of the scale. And I used the expressions that they proposed, but they didn't fit. They didn't fit some of my basic understanding. And also, of course, if I compare the 30 by 30 centimeters with the 80 by 80 centimeters, using this idea of scaling, it didn't work. So, well, at the end, a little bit of not a very good feeling of the entire story.
Thank you, Professor Alonso.
Professor Arbanas?
Yes.
Yes, Professor Di Maio would like to answer live to a question from Alessandro Gaio at 1 p.m. So could you pass the microphone to her? And could you read again the question from Alessandro Gaio too, please?
Yes, but I cannot see this question in chat.
It's a question from Alessandro Gaio at 1 p.m.
No, I cannot see it.
Yes.
I cannot see it.
If you want, I can read.
Yes, please.
Okay. A question for Professor Di Maio. Are your findings on higher permeability along the slip surface valid also for other slope failures in clay soils, or are they related to the presence of blocks in the clay matrix?
Then I can speak. Can I speak?
Yes, I can hear you.
Okay. Yes, I think that it's possible also in other landslides. However, I think that the main cause of higher permeability is the persistency, the continuity of the movement, because such a condition favors, first of all, a higher value of porosity along the shear zone, and then it favors the compression and even the opening. It depends also on the stress level of other discontinuities, those all the shears around the main slip surface, and among the irregularities that favors the opening or the increase in porosity, there is also the presence of fragments. That was just an example, because we observe it on the shear surface of specimens in laboratory after shear to the residual condition, after long shear, and so I did that example, but it's not the only cause. the main cause is the persistence and the continuity of the shear movement that allows the compression of any existing fissure discontinuity, I think, favored by irregularities such waveness, blocks, fragments.
Okay, thank you. I have one question, I think also for Professor Essa Di Maio, maybe for Farzanek, but it is part of the same team. I think that the presence of salt is very important in this presentation. And we also have here in our region some landslides. One is Salt Creek, another one is Slovenia, it is Salt Mud. There is another one, as I know, in Colorado, also Salt Creek, etc., etc. Do you know origin of this salt? It is one question. And the second is, did you make analysis about mineralogic composition of this material?
Yes, the origin is clear because the tectonized clay shales of which we are talking are marine origin soil, and at small depths from the ground surface they still have the original pore fluid. The marine seawater is a composite concentrated ion solution, and thus that is the origin in our case. We analyzed the mineral composition of the soils, and the main clay minerals, in the case of Costa della Gaveta, are illite and kaolinite, but somewhere in the slope, large percentages of smectite can be found. And in general, in tectonized clay shales along the Italian Apennine, smectite is an important component. The response of the different clay minerals to salt variations are different, as Farsane tried to show, but always a decrease in salt concentration causes a decrease in strength. Sometimes in the presence of swelling material, it can cause swelling or high values of swelling pressure.
Okay, thank you.
You're welcome.
Is there any other question? I am not the only one professor here, and
okay. I think that we are hungry now.
Yes. Okay, we have about 2 minutes to the end of this session, and I think that we can conclude this session. Thank you for all invited speakers, to all presenters, to audience, and to all that contributed to this discussion. I think that this symposium will go very well on, and I wish you that we will hear really good presentation this afternoon. Thank you again.
Thank you.
Thank you so much, Professor Arbana, for his work. So for your work and for your work of conveners and for your work of chairman. So see you to the next meeting at 2:15, entitled Monitoring.